Okay, and we're recording. All right, welcome back. Good evening, good morning. Another weekly review, and I'm going to continue over chapter 8, which is chapter 8 over friction. Because I think I did a few last time, so I'm gonna do a few more before I continue on to the next chapter. All right, so let's dive right into it. That was weird. All right, so I'm going to start off with 816. 816. That's kind of fair. Let's make this a little smaller. All right, so 816 is basically a ladder situation. So I'm gonna draw it out first while I read it. Uh, so that's something like this. So that's a ladder there, and there's a person on the ladder. I guess like this. All right, they give us the length of the ladder like this. I call this down here point A, this point B. This guy has a center of gravity. This right here is 10 feet, 3 feet. Okay, so there's a guy standing on a ladder. It says a 180-pound man climbs up the ladder and stops at the position shown, that position there, after he senses that the ladder is on the verge of slipping. And so he started at the bottom. He started at the bottom here. He walks up and then he stops right there because he feels that the ladder is starting to slip and slide back. Determine the inclination theta. So theta right here, which is the angle that the ground makes with the ladder. My pin back, this angle here. So we're trying to find that theta if the coefficient of static friction between the friction pad A and the ground. So there's a friction pad at A. So they give us basically this value here, 0.4. Assume B is smooth. So smooth at B, at A there's some friction. The center of gravity is of the man is at G. Okay, got that. Neglect the weighted ladder. All right. So we're just trying to find that theta there because it's on the verge of slipping, which means it's about to slide back to the right. So let's do a free body diagram first. I'm just going to use that picture, and then I'm going to use the red for those forces. So start at B. We know there's going to be a normal force off of the wall. Let's call that NB. And then for A, there's also going to be a normal force off of the ground. Let's call that NA. Then also at A, there's some friction, right? That's to the left because it's preventing the person from sliding to the right. So there's some friction this way. Let's call that force at A. Yeah, and then we also got the weight of this guy here. So his weight pulling downwards, which is 180 pounds. Okay, so yeah, that's it. That's it for our full body diagram now. And put this ladder in orange. So let's start off with some of the forces in the y direction. And of course, we could do some of the forces in the x direction as well. But I don't think that's going to get us anything. Let's do some of the forces. Let's just do both. All right, let's see what that says. So the sum of the forces in the y direction and the sum of the forces in the x direction. Both of those equal to 0, right? So sum of the force in the x direction, we got this normal force at A and minus his weight, which is 180. Okay. Some of the forces in the x direction, I might have mixed up my words there. Yeah. C and B, and what's that? Minus FA. Okay. So we see here now, that NA is equal to 180, and NB is equal to FA. Okay, now let's also do the sum of the moments. Let's do it at point B. All right, so what is 0? Call that direction positive, so that's equal to a B. We don't have to worry about that normal force at B, but we do have to worry about the weight there. All right, so I'm looking at this here. Draw like here to here. There's this force downwards. All right. Oh, and we also know this distance from here to here is 3. Okay. So that's just 3 and 180 then. And it's going to be minus because it's going in the negative direction. Okay. So what else did it tell us? It tells us this is 10 feet. So I guess we also have to do the moments for NA and FA. Okay, so it looks like that's going to be also minus sine, yeah, because that's, oh, well, this distance is 10. I see. So, 180, 10 sine, yeah. All right, because we have that component for this 180 is basically MA. That's right. That's MA. Yeah. Okay. And then I guess we have to do FA too. So it's gonna be plus 180. So cosine theta. Yeah. Oh, actually, what I'm missing is um, this friction at A here. FA is equal to friction. And friction is basically US times the normal force at A. We know the normal force A is 180, so FA is equal to that's whatever that's supposed to be. I see where I messed up at. That's what this is missing. This is missing that 0.4 here. Right. So I made a mistake here. This here is NA. This here is FA. There we go. Because we're doing a moment about B, so yeah, I think this one obviously is that force. Okay. So it looks like we're trying to solve for theta. So it looks like if I work this out, if I work this guy here out, that my calculator. I can actually do something like this. Alright, and let's divide everything by 10. So something like that, right? So it looks like we end up with something like this. 3 over 10 is 0.3. Alright, that's just 0.3. Okay. So yeah, we can solve this. Alright, if I just add, let's see what I can do. Actually, I think we can just put this into the computer and it'll solve it for us. Trying to think of some algebra we can do. Let's see. Okay, so yeah, let's put that into Wolfram alpha. And I get a 52 degrees for theta. Okay, that sounds about right. So basically, as he walks up this ladder, once that angle hits 52 degrees, if he steps up any further, the ladder is going to start to basically slide back this way. Okay. Cool. That wasn't so bad. I almost forgot about this part. We've got to use this friction. And again, we're able to do that because we know this static coefficient. All we have to do is really solve for NA. And solving for NA was the first thing we did. So that's the normal force at A. Okay, so that's related to the friction at A. Okay, and then we just took the moments about B to kind of analyze that angle. So we got that. right, let's do the next one. Let's do. I should have had this picked up beforehand, but I didn't. Let's go with number 23. That one looks cool. So number 23 looks like this. All right, there we go. So it looks something like that. That structure with a pin in it and a ball on the other side at an angle. And there's an external force pointing downwards here, directly at the center. I call it P. This is 2 meters. This is 2 meters. From here to here and here to here. I call this point over here A. This point over here is B. So the beam is supported by a pin at A and a roller at B, which has a negligible weight and a radius of 15 millimeters. Okay, so they're telling us about the little ball here. Let's zoom in on that. So this guy here has a radius. Okay, and if the coefficient of static friction is UB equals UC equals 0.3, determine the largest angle. So they're basically saying the coefficient of static friction is equal to this. It's the same for both the surface B and C, so that's the surface in between here, this surface here. I guess they're calling like the top B and the bottom here C. Right down here, C. So determine the largest angle theta of the incline so the roller does not slip for any force P applied to the beam. So what's the biggest angle that this can be at for the, you know, a value of P? It's interesting. So find max angle, you can write that down. Find theta incline. So roller doesn't slip. For any P. There we go. Okay. So we kind of have to look at this roller, this zoomed in picture of the roller here. And I guess I'm looking at it this way. is going to be like a normal down this way. And then like on the bottom, there's going to be a normal. I guess it's like a normal force from that's gonna be like this. There we go. So normal force from B, and right here, so normal force from C, and this is the bottom surface as well. Alright, there's a bottom surface right here, like that. Okay, and basically there's friction, right? Ah, I see what's going on now. There's friction on both of those surfaces. And so the ball wants to slide down, so the static friction is this way. Then there's another static friction this way. Yeah, okay. That's interesting. So yeah, let's label both of those. Let's call this force C. This is force B. And of course, we already know that force C is going to be equal to, well, let's just call this mu. And force B is going to be mu normal force B. Okay, so far so good. Um, let's see what else can we say. I think we can use this angle over here somehow. That's big theta. Let's see how it can. Yeah, okay. So I think I kind of see what's going on. Some geometry happening. Switch colors. So if this whole thing is draw dotted. So let's draw like a line from here down, straight down, kind of like that. And I think if we do that, then that theta must be the same. If I do that down, this here would be theta. Right, because this here is also a theta. Yeah, that makes sense because this goes to a corner. I guess some goes something like that. All right, you're saying this is theta, so that down there is theta, so that's theta. Okay, that all checks out. Mm, yeah, okay. I think that should work. So if I do the moments about, go to the center of the ball here. I call that center right here. Call that let's see if I do the moments about there. Well, I guess I'm doing it about O because the normal forces wouldn't matter, right? Because they pass straight through the center. But FB and FC don't, so there would be some moments for those, okay? And they're both the same distance away, right? Because the radius, but they're in different directions. Okay, so FB then would be the positive one. So we got the radius, which is 15, and FB. Okay, minus the other one, 15 FC. Okay, so that basically just tells us that FB equals FC. Okay, interesting. Does that also mean NC equals NB? I think it does. Let's keep going now. So let's try now the sum of the forces in the x direction. I think this might be a little tricky. Sum of the forces in the x direction. I guess NB is not in the x direction, so we don't worry about that. FB is in the negative, so I guess negative FB. Negative cosine component of FC. And the positive component. That gets that it's like sine plus NC sine theta. Because I'm looking right here. Alright, if we want the x component of that, we actually have to use sine, right? At that angle, okay. So what does that tell us? Well, I'm just leave it as is. I'm not sure yet. Let's keep going. Some of the forces in the y direction. Some of the forces in the y direction. So I got NC cosine theta plus FC sine. Yeah, it's weird that they're flopped, right? Minus MB. Okay, so I know FB equals FC, so I should be able to set these two guys equal. That's MB. Let's see. What's dog say? Should be able to combine these two equations. Let's see. Well, they're both equal to 0. I guess I'm gonna do it like that. But yeah, I could just say this is FB. sine theta minus FC. Can I just plug it in? I'm overthinking this too. NC. Yeah, the same thing. Oh, I see. Okay. FC. Sine theta. Okay, so I should be able to get to this. So NB. Yeah, NB is. I swear. I know it's doing that thing again. I'm gonna have to refresh real quick.